Hello guys, today we will discuss about chapter number 2, electrochemistry. Part 1, electrolytic conductance and transport number. Electrolytic and metallic conduction and a factor affecting them. Electrolytic and metallic conduction. Substances which allow electricity to pass through them are known as conductor, whereas substances which do not allow electricity to pass through are known as insulator. Conductors are divided into two categories. First, those which conduct electricity without undergoing any decomposition. These are electronic conductors, example metal, graphite, and certain minerals. As the name indicates, the conductor in the case is due to the flow of electrons. Second, those which undergoes decomposition when current is passed through their aqueous solution or a molten. They are known as electrolytic conductions or electrolytes. Example, solution of acid, bases and salts in water and fused state, etc. In this case, the flow of electricity is due to the movement of ion. Electrolytes are further classified into two main categories as strong electrolyte and weak electrolyte. Strong electrolyte are the substances like strong acid, example HCl, HNO3, H2SO4, etc. Strong bases, example NaOH and KOH, etc. and most of the inorganic salts. These dissociate almost completely in the aqueous solution or in the molten state and hence conduct electricity to a large extent. Weak electrolyte and a substance like weak acid, example ethanoic acid, HCN, H2CO3, H3PO4, etc. and weak bases, example ammonium hydroxide, calcium hydroxide, aluminium hydroxide, etc. These have low degree of dissociation and hence conduct electricity to a small extent. Substances like sugar, urea, etc., the solution of which do not conduct electricity are known as non-electrolytes. Factor affecting electrolytic conduction. The conduction of a solution of an electrolyte depend upon the following factors. First, interionic attraction, which depend upon the interaction between the ion of solute and hence are called solute-solute interaction. On this basis, the substances are classified as strong electrolyte and weak electrolyte as already mentioned. Second, solution of ion which depend upon the interaction between the ion of solute and the solvent and hence are called solute-solvent interaction. Third, viscosity of a solvent which depend upon the solvent-solvent interaction. The effect of all these factors are described with increase or over temperature. Hence, the electrolytic conduction increase with increase of a temperature. On the other hand, the electrolytic conduction of the electronic conductors decrease with increase of a temperature. Alternate. The factor on which the electrolytic conduction depend are as follows. First, nature of electrolyte. Strong electrolyte ionized almost completely in the solution and hence conduct electricity to a large extent, whereas weak electrolyte ionized to a small extent and hence conduct electricity also to a small extent. Nature of solvent. Electrolyte ionize more in a polar solvent, hence greater is the polarity of the solvent, greater is the ionization and hence greater is the conduction. Third, concentration of a solution. Here the concentration of the solution less is the conduction. This is because in a weak electrolyte the ionization is less, whereas in a strong electrolyte the interionic attraction are high at high concentration. With dilution interionic attraction decrease in conduction increase. Temperature. On increasing the temperature the dissociation increase and hence conduction increase. Difference between metallic conductors or electrolytic conductors. The main point of a difference between metallic conductor and electrolytic conductor can be suggested up in table 2.1. Metallic conductor. Flow of electricity takes place without the decomposition of substance. Electrolytic conductors. Flow of electricity takes place accompanied by the decomposition of a substance. Second, flow of electricity is due to the flow of electron only, such that there is no flow of a matter. The conductance depend upon the structure and the density of a metal and the number of valence electrons per atom. Flow of electricity is due to the movement of ion and hence there is a flow of a matter. The electrical conductance described with increase of a temperature. This is because kernels start vibrating, which produce hindrance in the flow of electrons. The electrical conduction increases with increase of a temperature. This is generally due to increase in dissociation or degree in the interionic attraction. The resistance offered by the metal is also due to vibrating canals. The resistance of by electrolyte is due to the factor like interionic attraction.
On increasing temperature, the frequency of vibration kernel increases. Fifth, electrolytic conduction increases with temperature. This is due to increase in dissociation of electrolyte and decrease in interionic attraction with increase in temperature. Electrical resistance and conductance. Electrolytic solution conduct electricity through them by the movement of ions towards the electrolyte. Like metallic conductors, electrolytic conductors also offer resistance to the flow of electricity. Hence, electrolytic lights are also obey Ohm's law. According to Ohm's law, current I flows through a metallic conductor is directly proportional to potential difference across it. I is directly related to V. I is equal to V by R. V is equal to IR, where R is constant of proportionality and is known as resistance of conductor. It is referred in ohm and is represented as the symbol, which is ohm. Current is generally measured in ampere and potential difference is measured in volts. According to Ohm law, ohm is equal to volt by amperes. Unit of resistance is ohm. In terms of SI unit base, ohm is equal to kg meter square by s cube a square. The unit of ohm can be obtained as ohm is equal to V by A, work per unit charge by A, work per unit charge into 1 by A, work is force into length, and change is A into S into 1 by A, which on further calculating we will get kg meter square s cube a square. From Ohm's law, it follows that a substance which offers lesser resistance will allow more electricity to pass through it. Thus, conductance is reciprocal of resistance. It is represented as C, which is equal to 1 by R. Unit of conductance is reciprocal of ohm, ohm inverse or mho. Ohm is abbreviated as the symbol ohm, so the ohm inverse may be written as ohm inverse, as this symbol is showing. Electrical conductance is also expressed in Simon S, named after noted electrical engineer Sir William Simon. Specific conductance, equivalent conductance, and molar conductance. Specific conductance. The resistance R of a conductor is directly proportional to length L and inversely proportional to its area of cross section A, as shown by the expression where rho is the constant of proportionality and which is known as specific resistance or resistivity. Value of rho depend upon nature of conductor. From equation 1, we have rho is equal to R into A by L ohm centimeter square by centimeter, which will equal to ohm centimeter. L is 1 centimeter, area is 1 square centimeter, then rho will equal to R. The specific resistance or resistivity is defined as resistance of conductor of 1 centimeter length and having area of cross section equal to 1 centimeter square. In other words, resistivity of specific resistance is the resistance between opposite faces of 1 centimeter cube of a conductor. Unit of resistivity are ohm centimeter. Its SI unit are ohm meter. 1 ohm meter is equal to 100 ohm centimeter or 1 ohm centimeter, which is equal to 0.01 ohm meter. The reciprocal of specific resistance is known as specific conductance. It is denoted by kappa. Thus, kappa is equal to 1 by rho. Kappa is equal to 1 by R into L by A. kappa will equal to C into L by A. If length is 1 centimeter, area is 1 square centimeter, then kappa will equal to C. Hence, specific conductance is defined as conductance of a solution of 1 centimeter length and having 1 square centimeter as the area of cross section. In other words, specific conductance is the conductance of 1 centimeter cube of a solution of an electrolyte. The unit of specific conductance are derived as follows: kappa is equal to 1 by A into L by R is equal to 1 by ohm into centimeter by centimeter cube. Then we will get the unit as ohms inverse, centimeter inverse, or S centimeter inverse. In SI unit, the area of cross section is expressed in meter square and length is expressed in meter. The unit of specific conductance are S meter inverse or ohm inverse meter inverse. 1 ohm inverse centimeter inverse is equal to 100 ohm inverse meter inverse, and 1 S in centimeter inverse is equal to 100 centimeter inverse. Equivalent conductance: the current is an electrolyte is carried by ions. A particular volume of a solution may contain more or less ions depending upon its concentration. Therefore, the conductance of an solution varies with concentration. So, for comparing the conductance of a different solution, it is required that they should have some volume and must furnish amount of ions carried some total charge. This can be achieved by taking equal volume of solution containing their respective gram equivalent masses. The conductance of such solution is called gram equivalent conductance. Equivalent conductance may be defined as the conductance of a solution carrying 1 gram equivalent of electrolyte dissolved in volume V centimeter cube of solution, such as the whole of solution is placed between two electrolytes 1 centimeter apart. It is denoted by symbol lambda. Equivalent conductance representing the conductivity power of an equivalent of the given electrolyte at the given dilution or conduction and temperature. Molar conductance of a solution at dilution V is defined as the conductance of all the ions produced from 1 mole of electrolyte dissolved VCC of solution, such the whole of the solution is placed between two parallel electrolytes 1 centimeter apart. It is denoted by lambda m. Relationship between molar conductance and specific conductance. Molar conductance of a solution is obtained by multiplying the specific conductance by volume in Cc, which contains 1 mole of electrolyte. Thus, delta M is equal to K into V, where V is the volume of solution in centimeter cube containing 1 gram mole of the electrolyte. If a solution contains C moles of electrolyte in 1000 cc of solution, then the volume of the solution containing 1 mole will be 1000 per cc. Thus, above expression can be written as delta M is equal to K into volume in centimeter cube containing 1 mole of electrolyte. Delta M is equal to K into 1000 by C, which is equal to K into 1000 by molarity. Hence, K is specific conductance and C is molar conductance, that is mole per liter or mole dm cube. Calculation for equivalent conductance. Equivalent conductance and specific conductance are related to each other as delta equivalent is equal to K into 1000 by C equivalent, where C equivalent is concentration in gram equivalent per liter, the normality of solution. Thus, knowing specific conductance and normality of solution, we calculate equivalent conductance of the solution. variation of conductance, specific conductance, and equivalent and molar conductance with dilution. Generally, the electrolytic conductance decreases with increase in concentration or increases with increase in dilution. It is because the conductance is due to presence of ions in solution. The greater is the number of ions, greater is the conductance. With dilution, more ions are produced in solution, so conductance also increases on dilution. The specific conductance is the conductance of a 1 centimeter cube of solution on dilution. The specific conductance decreases because the conduction of ions per centimeter cube decreases, and thus the specific conductance decreases. On the other hand, the molar conductance and equivalent conductance increases on dilution. This is because the molar conductance and equivalent conductance are the product of specific conductance and volume of solution containing 1 mole or 1 gram equivalent of electrolyte. Delta is equal to K into V. On dilution, the specific conductance decreases with the increase in volume is much more than decrease in specific conductance. As a result, molar conductance and equivalent conductance increases with dilution. Calculation for equivalent conductance. Equivalent conductance and specific conductance are related as delta equivalent is equal to K into 1000 by C equivalent, where C equivalent is the concentration in gram equivalent per liters, that is normality of solution. Thus, knowing specific conductance and normality of solution, we calculate equivalent conductance of solution. Variation of conductance, specific conductance, equivalent and molar conductance with dilution. Generally, the electrolytic conductance decreases with increase in concentration or increases with increase in dilution. This is because the conductance is due to presence of ions in solution. The greater is the number of ions, greater is the conductance. With dilution, more ions are produced in solution, so conductance also increases on dilution. The specific conductance is the conductance of 1 centimeter cube of solution. On dilution, the specific conductance decreases because the concentration of ions per centimeter cube decreases, and therefore the specific conductivity decreases. On the other hand, the molar conductivity and equivalent conductivity increases on dilution. This is because the molar conductance and equivalent conductance are the product of specific conductance and volume of solution containing 1 mole or 1 gram equivalent of electrolyte. Delta is equal to K into V. On dilution, the specific conductance decreases, but the increase in volume is much more than decrease in specific conductance K. As a result, molar conductance and equivalent conductance increases on dilution. Section 2. Theories of electrolytic dilution and Ostwald dilution law. 3.08 Arrhenius theory of ionization. Arrhenius studied the conductance of aqueous solution of different electrolytes. He proposed that the conductance of solution was due to the presence of ions. Arrhenius put forward this theory of ionization in 1884. Arrhenius theory of ionization is summarized as follows. An electrolyte, when dissolved in water, splits up into charged particles called ions. The positively charged particles are called cation, negatively charged particles are called anion. In modern view, the theory associated with the electrolytes are already ionized in the solid state, and these ions are held by electrostatic forces. When the electrolyte is dissociated in water, the electrolyte dissociate to form separate cation and anion. Thus, AB is equal to A plus B minus old form. A plus B minus will equal to A plus B minus modern form. For this reason, this theory is also called theory of electrolytic dissociation. Second, the charge carried by cation is equal to the charge carried by anions. As a result, the electrolyte solution is electrical neutral. Third, the charged ions move through the solution towards the oppositively charged electrodes. This migration of ions causes the passage electric current through the electrolytic solution. This explains the conductance of electrolyte and the phenomena of electrolysis. Fourth, the electrolyte may be completely ionized. The ratio of dissociation molecules to the total number of molecules is called the degree of dissociation, denoted by alpha. Thus, degree of dissociation is equal to number of mole dissociated by total number of molecules. The ions formed in the solution constantly reunite to form undissociated molecules. Thus, a state of equilibrium exists between the undissociated molecules and the ions formed by the dissociation of electrolyte. AB in equilibrium will give A plus B minus. The equilibrium constant for this equilibrium is written as K is equal to A plus closed in brackets B minus closed in brackets, which is the concentration of A plus and B minus by the concentration of AB, where K is called dissociation constant. The degree of dissociation increases on dilution and become maximum at infinite dilution. The electrical conductance of an electrolytic solution depends upon the number of ions present in the solution. Thus, the degree of dissociation of an electrolyte determines whether it is a strong electrolyte or a weak electrolyte. Limitation of Arrhenius theory. Although Arrhenius theory could successfully explain the behavior of weak electrolyte, yet it could not explain various observed facts about strong electrolytes. Some of the important limitations of this theory are as follows. According to Arrhenius theory, ionization of electrolytes takes place in aqueous solution. However, Bragg in 1912 through X-ray diffraction studies shows that many electrolytes are ionized even in their crystalline state, that is Na plus Cl minus. Second, strong electrolytes conduct electricity even in molten state. So the ionization of electrolyte takes place even in the absence of water. Thus, Arrhenius theory could not explain the role of water in dissociation of electrolytes. Ostwald dilution law, which is based on Arrhenius theory, fails for strong electrolytes. The values of equilibrium constant for dissociation of strong electrolyte were found to vary with the concentration of electrolytes, that is a constant value of dissociation constant Kd is not observed. There is good agreement between degree of ionization calculated from the conductivity measurement, that is alpha is equal to delta by delta, and the one calculated from measurement of colligative property only for univalent electrolytes like NaCl, but marked disagreement in the value of alpha was found for bivalent electrolytes such as CuSO4, HgSO4, etc. Ostwald dilution law, ionization of weak electrolytes. It has been mentioned earlier that weak electrolytes are ionized only partially. According to Arrhenius theory of ionization, the ionic formed as a result of dissociation of weak electrolytes are present in dynamic equilibrium with undissociated molecules. Consider the ionization of a binary weak electrolytes. AB in equilibrium will give A plus plus B minus. In 1988, Ostwald applied law of chemical equilibrium to such chemical equilibrium and obtained a relationship between Ostwald's dilution law. Let C moles per liter be the concentration of electrolytes in solution and alpha be the degree of dissociation. The concentration of various species at equilibrium would be as under. AB aqueous in equilibrium will give A plus plus B minus. Initial concentration in reactant site is C but there is no initial concentration in product side. Equilibrium concentration in reactant side C minus C alpha. In product side C alpha and C alpha of both the products. C minus C alpha can be written as C taking common into 1 minus alpha. Applying law of chemical equilibrium, Kd will equal to concentration of A plus and concentration of B minus by AB concentration. On putting their values, we will get Kd will equal to C alpha square by 1 minus alpha. Exact form, that is, let equation number 1. When Kd is the dissociation constant of electrolyte AB, like any other equilibrium constant, Kd is constant only at a constant temperature. For weak electrolyte at ordinary concentration, alpha is very less than 1. Therefore, alpha can be neglected in comparison to 1 in the denominator of expression 1. Then the specified formula becomes Kd is equal to C alpha square will equal to Kd by C, alpha will equal to under root Kd by C. Expression 1 and 2 are the form of Ostwald dilution law. Expression 2 can be written as expressed as alpha is directly related to under root 1 by C. From equation 2, it is obvious that the degree of dissociation alpha increases as C decreases. As C approaches 0, alpha approaches 1. Thus, Ostwald dilution law may be studied as for a weak binary electrolyte, the degree of dissociation is inversely proportional to square root of molar conductance. Further, as C is the concentration in moles per liter, then the volume of V of solution containing 1 mole of electrolyte will be 1 by C liters, that is V is equal to 1 by C. Equation 1 and 2 can then be written as Kd is equal to alpha square by 1 minus alpha by V, and Kd is equal to and alpha is equal to under root Kd V. Also, Kd is equal to alpha square by 1 minus alpha V. If the values of Kd are found to be constant, the Ostwald law is verified. Limitation of Ostwald dilution law. Its limitations are expressed as: first, Ostwald dilution law holds good only for weak electrolytes in dilute solution and fails completely in case of strong electrolytes like HCl, NaOH and salts, etc. Ostwald law is based on Arrhenius theory of dissociation, according to which only a factor of electrolyte dissociate at ordinary condition and complete dissociation occurs only at initial dilution. This is true only for weak electrolytes, as strong electrolytes are almost completely dissociated at all concentrations. Hence, the formula delta C by delta naught does not give correct value of alpha. Here this table 3 shows the dissociation constant for acetic acid and KCl at various concentrations using Ostwald dilution law. Application of Ostwald dilution law. Ostwald dilution law is applicable only for weak electrolytes. It is used in calculating the dissociation constants Kd of weak acids and weak bases by determining the degree of dissociation from conductance measurement at a given concentration C. Using the calculated value of Kd for a weak acid or a weak base which is constant at a particular temperature, the degree of dissociation of that weak electrolyte can be determined at any concentration C. Transference number or transport number. During the passage of electric current through an electrolyte, the ions migrate through electrolytes. Thus, the current is carried by an anion and cation. The current carried by an ion is directly proportional to the speed of ion. The higher the speed of ion, more is the current it carries, and hence greater is its transport number. The fraction of the total current carried by an ion is called transport number, transference number, and Hittov's number. If UC represent the speed of cation and UA of anion, then current carried by cation is directly related to UA, which is equal to KUA. Same for anion is directly related to UA, which is equal to KUA. Total amount of current carried is equal to KUC plus KUA, which is equal to KUC K bracket UC plus UA bracket close. Transport number of cation NC is equal to KUC by K bracket UC plus UA. TC is equal to UC by UC plus UA. The transport number of anion Na is equal to KUA by KUC plus UA. TA is equal to UA by UC plus UA. Dividing equation 3 by equation 4. Then after solving this, we will get TC by TA will equal to UC by UA. By adding equation 3 and 4, we will get TC plus TA, which is equal to UC by UC plus UA plus UA by UC plus UA, which will further equal to UC plus UA by UC plus UA. After cancelling, we will get 1. Therefore, TC plus TA is equal to 1. That is the sum of transport number of cation and anion of an electrolyte is always unity. Hence, whole of the current is carried by the ions. Let the speed ratio of ions UC by UA be denoted by R. Then transport number of cation can be written in terms of R as follows. TC will equal to UC by UC plus UA, which is equal to UC by UA plus 1 plus UC by UA. Here we have divided by UA in numerator and denominator, which will equal to R by 1 plus R. Similarly, TA will equal to UA by UC plus UA, which will further equal to 1 plus 1 by UC by UA will equal to 1 by 1 plus R. TC is equal to UC by UC plus UA, which is equal to R plus 1 by R. TA will equal to UA by UA plus UC, which is equal to 1 by 1 plus R. Determination of transport number. There are two methods of determination of transport of an ion. First, Hittov's method. Second, moving boundary method. Hittov's method. Principle. This method is based on Hittov's rule. According to this rule, the fall in concentration around an electrode is proportional to the speed of the ion moving away from that electrode. Fall in concentration around cathode by fall in concentration around anode is equal to speed of anion by speed of cation will equal to UA by UC, or 1 plus fall in concentration around cathode by fall in concentration around anode will equal to 1 plus UA by UC, or fall in concentration around cathode plus fall in concentration around anode by fall in concentration around anode will equal to UA plus UC by UC. Therefore, total fall in concentration around both electrodes by fall in concentration around anode will equal to UA plus UC by UC. Inversing both the sides, we can write UC by UA plus UC will equal to TC. Expressing the concentration in terms of grams equivalent, we can write TC is equal to number of gram equivalent lost around anodic compartments by number of gram equivalent lost around both the compartments. The number of gram equivalent lost from both the electrodes is equal to the number of gram equivalent deposited or discharged at each electrode. This can be measured by placing an silver or a copper coulometer in series. According to Faraday's second law, when the same quantity of electricity flows through the silver or copper coulometer, the same number of gram equivalent of Ag or Cu will be deposited. Thus, Tc is equal to number of gram equivalent lost from anodic compartment by number of gram equivalent deposited in the coulometer. Knowing the value of Tc, the value of Ta can be found as Ta is equal to 1 minus Tc. From these equations, we can calculate transport number and hence the relative ionic mobility from measurement of fall in concentration during electrolysis. Measurement of transport number by Hitop's method. For the measurement of transport number, the apparatus should be such as: first, there should be three separate compartments: anodic, cathodic, and a middle compartment. During electrolysis, there should be no intermixing of solution of these compartments. The solution from any compartment can be withdrawn without disturbing the solution in other compartments. It is achieved by using a suitable apparatus in which the anode and cathode compartments are separated by middle compartment as shown in figure 13. It consists of two vertical glass tubes joined together through a U-tube in middle. At all the three tubes are provided with stop corks at the bottom. By closing these stop corks, the mixing of solution in the cathode and anode limbs can be stopped. The cathode and anode is made of platinum non-attackable electrodes. The cathode and anode may be made of Ag or Cu if the transport number of Ag plus or Cu2 plus ions is to be determined. A silver or copper voltmeter is placed in series with the solution so that the same quantity of electrical current passes through the procedure. The apparatus is filled with the electrolyte solution of the ions whose transport number is to be determined. The electrodes are inserted and the cell is connected in series with a silver or copper coulometer. The concentration of electrolytes is found by titrating the solution with a suitable reagent. A steady current of 0.01 or to 0.02 ampere is passed for 2 to 3 hours so as to produce appreciable change in concentration. After electrolysis, the stop corks of the U-tube are closed. The whole liquid in the anode compartment is carefully drained into a weight flask or its weight is determined. It is titrated to determine the weight of electrolyte present. The weight of silver deposited in silver coulometer or copper in copper coulometer is determined. There should be no change in concentration of solution in U-tube. The solution from the central compartment is taken out and the titration to know if there is any change in concentration of electrolyte. In case of concentration change is there, the experiment is repeated. Calculation. Case 1. When the electrodes are non-attackable, PT electrodes are used. After passing electric current, let the weight of an anodic solution taken W1 gram. Weight of AgNO3 found in to be present in it by titration will equal to W2 gram. Weight of water solvent present, that is equal to W1 minus W2 gram. W1 minus W2 of water contain W2 gram of AgNO3 after electrolysis, or W1 minus W2 gram of water contains W2 by 170 gram equivalent of AgNO3. W2 by 170 gram equivalent of a gram will equal to X. Say, before passing electric current, let W3 gram of solution contain AgNO3 will equal to W4 gram. Weight of water in solution equal to W3 minus W4 gram. Hence, before electrolysis, W3 minus W4 gram of water consists AgNO3 is equal to W4 gram. The weight of water remains unchanged after electrolysis. W1 minus W2 gram of water will contain W4 by W3 minus W4 into W1 minus W2 gram of AgNO3. W4 by W3 minus W4 into W1 minus W2 by 170 gram equivalent of AgNO3, which will further equal to Y gram equivalent of Ag. When electrodes are non-attackable, the amount of Ag or Cu deposited in coulometer X is less than the actual increase in concentration of Ag plus in the anodic compartment Y. So, X is less than Y. Therefore, fall in concentration in anodic compartment will equal to Y minus X gram equivalent of Ag. Let the weight of Ag deposited in silver coulometer will equal to Wg will equal to W by 108 gram equivalent of Ag, which will equal to Z gram equivalent of Ag. Transport number of Ag plus T by Ag plus will equal to fall in concentration around anode in gram equivalent by amount of Ag deposited in voltameter in gram equivalent will equal to Y minus X by Z. Transport number of NO3 negative T NO3 negative will equal to 1 minus T Ag plus. Case 2. When electrodes are attackable, Ag electrodes are used. In this case, there is increase in concentration around the anode because every NO3 negative reaching the anode dissolves one Ag plus ion to form AgNO3. Thus, X is greater than Y. The increase in concentration around the anode X minus Y gram equivalent of Ag. This increase in concentration of Ag plus ion around the anode takes place even when Ag plus ion migrate from anodic compartment if no Ag plus ion have migrated from the anode, the increase in concentration of Ag plus ions would have been equal to Z gram equivalent. Fall in concentration around anode due to migration of Ag plus ion will equal to Z minus bracket X minus Y gram equivalent of Ag. Hence, transport number of Ag plus ion T Ag plus will equal to Z minus bracket X minus Y by Z. Transport number of NO3 negative will equal to 1 minus T Ag minus will equal to 1 minus Z minus bracket X minus Y by Z. When copper coulometer is used in the experiment, the number of gram equivalent of copper deposited in the coulometer is obtained by dividing the weight of copper deposited by the equivalent mass of copper, that is 31.75. When electrodes are attackable. Moving boundary method principle. In this method, the migration of ions under the influence of applied potential is observed and the speed of anion and cation are determined. Then the transport number of cation and anion are calculated using the following relationship. Tc is equal to Uc by Uc plus Ua and Ta is equal to Ua by Uc plus Ua, where Uc and Ua are the speed of cation and anion respectively. Apparatus. The apparatus used is shown in figure 14. It consists of a long vertical tube mounted vertically and fitted with platinum electrode at both the ends. To determine the transport number of the ions of a given electrode Ma, two other electrodes M-A and Ma- each having an ion common with the experimental solute Ma are selected. The electrolyte solution M-A and Ma- act as indicator electrolytes, while Ma act as principal electrolyte. The solution of Ma is placed between the indicator solution to form sharp boundaries at A and B as shown in figure 14. The anode is inserted in solution of M-A and the cathode in the solution of Ma-. For example, if is KCl, then M-A can be LiCl and Ma- can be CH3COK, and the solution are placed in the order of increasing density downward to avoid mixing. The original boundaries are shown as A and B. In case of a colorless solution, the boundaries can be seen because the difference between difference their refractive index. To maintain sharp boundaries, the speed of indicator ion m dash must be less than that of m, and the speed of a dash must be less than a. In this condition of m dash ion do not overtake m ion at a, and a dash ion do not overtake a ions at boundary b, and sharp boundaries at a and b are mentioned. On passing electric current, the boundaries A moves to A dash while the boundaries B move to B dash. Thus, the speed of cation UC is directly related to distance AA dash, and speed of anode UA will equal to distance BB dash. Section 4. Coleridge Law. The law of independent migration of ions, its application or application of conductance measurement. Coleridge Law. Coleridge studied the molar conductance at infinite dilution for strong electrolytes. He found an interesting pattern between the values of delta node m for different strong electrolytes. It was observed that the difference of delta node m of different pairs of strong electrolytes having a common cation or a common anion was almost same. Consider the table 4. This table shows the delta node m values for some pair of strong electrolytes. It is observed that the difference between molar conductance of K plus and Na plus is 23.4 ohm per ohm inverse centimeter square mole inverse respectively of the ion. Similarly, difference between molar conductance of Cl negative and NO3 negative ion is 4.9 ohm inverse centimeter square mole inverse irrespective of the cation associated with them. Thus, it may be concluded that each ion makes a definite contribution to the molar conductivity at infinite dilution respective of other ions. The individual contribution of an ion toward total molecular conductivity of the electrolyte is called molar ionic conductivity. As a result of these observations, Coleridge gave a generalization called Coleridge law. It states that at infinite dilution, where the dissociation of electrolytes is completed, the molar conductivity of electrolyte is sum of limiting ionic conductivities of the cation and anion, each multiplied by the number of ions composing one formula unit of the electrolyte. Coleridge law for an electrolyte AXBY may be mathematically stated as delta node m AXBY will equal to x lambda node A plus y lambda node B minus, where x and y represent the number of positive and negative ions furnished by one formula unit of a electrolyte. Lambda node m AXBY is the limiting molar conductance of electrolyte AXBY, and lambda node A plus and lambda node B minus are the limiting molar conductivities of cation A plus and anion B minus respectively. For example, for NaCl, delta node m NaCl will equal to lambda node Na positive plus lambda node Cl negative. For KNO3, delta node m KNO3 will equal to lambda node K positive plus lambda node NO3 negative. For MgCl2, delta node m MgCl2 will equal to delta node Mg2 positive plus 2 lambda node Cl negative. Application of conductance measurement or applications of Coleridge law. The conductance measurement have many applications in theoretical as well as analytic chemistry. Some of the applications are discussed as follows. First, degree of dissociation of a weak electrolyte. Arrhenius theory assumed that in case of weak electrolyte, the increase in equivalent conductance on dilution is due to increase in the degree of dissociation of electrolyte. It is evident that when limiting values of equivalent conductance is approached, the degree of dissociation is unity. Thus, the degree of dissociation is given by alpha will equal to delta C by delta naught, where delta C is equivalent conductance at any concentration and delta naught is equivalent concentration conductance at infinite dilution. It may be noted that above relationship holds only for weak electrolyte. The value of delta naught for strong electrolytes can be calculated using Coleridge law. Dissociation constant Ka of weak acids. Consider the dissociation of a weak acid Ha having initial concentration as C moles liter. Let alpha be its degree of dissociation. Thus, we can write Ha in equilibrium will give H positive plus A negative. Initial concentration is C mole inverse, whereas of product is 0. Equilibrium concentration C into 1 minus alpha, and on product side will give C alpha. Applying the law of chemical equilibrium, the dissociation constant Ka of a weak electrolyte can be written as Ka will equal to concentration of H positive into concentration of A negative by concentration of Ha. On putting the values, we will get C alpha square by 1 minus alpha. The value of alpha can be calculated from equivalent conductance. Alpha will equal to delta C by delta naught. Substituting the values of alpha in expression 1, the dissociation constant Ka for weak acids can be calculated. Solubility of sparsely soluble salts. Salts such as AgCl, PbSO4, BaSO4, etc. dissolved to a very small extent in water and therefore are called sparingly soluble salts. Since they are very slightly soluble, their solution may be taken as infinite dilute. Moreover, because their solution are saturate, their concentration may be taken equal to their solubility. Thus, by determining the specific conductance and equivalent conductance of such solution, we can easily calculate solubility as, let S be the solubility of sparingly soluble salt in gram equivalent per liter, then the volume of the solution in cc containing 1 gram equivalent of salt will be 100,000 by S. Equivalent conductance and specific conductance of such solution are related as delta will equal to kappa into 1000 into S. As the salt is sparingly soluble, its solution may be taken as infinite dilute. So, delta may be taken as equal to delta naught. Thus, we can write delta naught will equal to kappa into 1000 into S. S will equal to kappa into 1000 into delta naught. Delta naught can be found by applying Coleridge law. To calculate solubility in gram liter, the quantity S is multiplied with the equivalent mass of the salt. Determination of solubility product of a sparingly soluble salts. Let us consider the general case of sparingly soluble salt, say AB. When this salt is dissolved in water to give a saturated solution at a particular temperature, there exists an equilibrium between undissolved salt and the ion A plus and B minus in solution. This can be represented as AB solid in equilibrium with water will give A plus aqueous plus B minus aqueous. Kc will equal to concentration of A positive into concentration of B negative by concentration of AB solid. Since the molar concentration of solid is taken to be constant, say K, we can rewrite this equilibrium as Kc into K will equal to concentration of A positive into concentration of B negative, or KSP will equal to concentration of A positive into concentration of B negative, where Kc into K is equal to KSP is known as solubility product, and it is equal to the product of ionic conductance for an constant solution. For a sparingly soluble salt AXBY, which dissociate to give set up equilibrium, AXBY in equilibrium will give X A raised to power Y plus Y B raised to power X minus. The solubility product may be expressed as KSP will equal to A raised to power Y plus concentration whole raised to power X, concentration of B raised to power X minus power Y. If S represent the concentration or solubility of sparingly soluble salt AXBY, then from the above equilibrium we have AY plus will equal to XS, Bx negative will equal to Ys, KSP will equal to concentration of XS raised to power X into concentration of Yx raised to power Y. Example, for calcium phosphate Ca3PO4 whole twice, X is equal to 3, Y is equal to 2. KSP will equal to 3s cube into 2s square will equal to 9s cube into 4s square will equal to 36s5. Now, solubility S of sparingly soluble salts can be determined by conductivity measurement as explained in application number 3. Thus, the solubility product of the salt can be easily evaluated provided solubility is known. So, our chapter